The ambiguous case. If I wanted to solve for theta, and this was the only information I have, if you remember all the way back to learning about congruent triangles and how to prove that two triangles are congruent, you had a lot of different ways to prove whether or not a triangle was congruent, right? You had side angle side, you had angle angle side, you had HL, you had side side side. And one thing that you learned was that angle side side is not a good way to prove that two triangles are congruent because it's not true. You cannot prove if you have an angle next to a side next to a side, you cannot prove that two triangles are congruent. And notice the information I'm given here is an angle next to a side next to a side. And the reason why I can't prove that two triangles are congruent given that information is because it does not make a unique or only one triangle. I could, if I wanted to, have this side moved because that angle is not solidified. That angle could be anything. That angle could be this, that angle could be this, that angle could be this. I don't know what that angle is. The only thing that is solidified is this angle next to this side. And similarly, this side length could be shorter or it could be longer. There is one other way to build this triangle with this information. If I pivot that 9 centimeter and bring it in like this, that 9 will hit that side again, and I haven't changed anything about the information I'm given. I still have a 60-degree angle, 10 centimeters here and 9 centimeters here. These guys would be equal. This would also be theta because that makes an isosceles triangle, and it always does in that relationship. So then also, theta here, this could be theta. So there's two answers here for theta. It could be the acute angle theta, which if you use numerical solve in order to solve for this, it will always give you the acute angle, not the obtuse angle. And then if I wanted to solve for the obtuse angle, it's actually just added with the first angle up to 180 because they create one line. This is complicated. This is tough. And the reason why we're not spending a whole lot of time on it is because you in SL don't have to worry about it. In HL, they do. So in SL, we will never be given an ambiguous case. If you go into your guide for this class, it says specifically like you will never have an ambiguous case on the test. Only HL will. So that's why numerical solve technically only gives you one of the two correct answers. It always gives you the smallest one. We have to know, we don't have to. Some people have to know that like there's more than one correct answer for some of these cases, not all of them, only when it's angle side side and only then some of the situations that are angle side side, it gets complicated, but we don't have to worry about it. And that's our only answer in this class. All right, for the cosine rule, I would like for you to again draw another triangle that is a non-right triangle because we are only going to use sine and cosine rules on non-right triangles, even though technically you can use them on right triangles as well. We're just not going to muddy the waters. Once you're done drawing your triangle, I would like for you to label it with capitalized A, B, and C, and then label its opposite side lengths accordingly. The cosine rule, again, relies on this relationship of an angle and its opposite side. So its formula is saying, hey, we're talking about an angle and its opposite side and these other things. It doesn't necessarily have to be a side length of A or an angle of B. So C squared equals A squared plus B squared minus 2AB cosine of C. The things you have memorized in your brain when you're a math teacher are like amazing. So that is in your formula packet as well, and it's only written in this way. The main key point about the cosine rule is that it's a side length here, side length of C, which is the opposite of the angle that you put into cosine. Besides that, it doesn't matter which one's A and B because they are treated the same. Adding these two together, it would be the same as B squared plus A squared. And multiplying these together, that's the same as B times A. So the only key important part about the cosine rule is the side length out here needs to be opposite of the angle that's in here. So I could rewrite this as B squared equals a squared plus c squared minus 2ac cosine of b. Or I could write it as a squared equals b squared plus c squared minus 2bc cosine of a. The thing that's important is side opposite of the angle, side opposite of the angle. So just keep that in mind, that it doesn't have to be C here. It's just the relationship idea of an angle and its opposite side. Notice that in your formula packet, it also gives you this. This is super helpful for solving for angles. Okay? Angle that you want to solve for, and then all of the side lengths that go in here. Because once we have cosine of an angle isolated, we can then use our inverse to flip them around. So that's going to be helpful for solving angles, and we will practice that in example 4. But let's go ahead and first practice this guy. So as we are solving for side lengths, using the law of cosines, we are looking for an angle and its opposite side. Once you establish that, then you know which side length should go on the other side of the equal sign. Because if I'm going to plug in cosine of 30 over here, then the side length opposite of that should go on this side of the equal sign. So that has to be x squared because the angle I'm plugging in is 30. Besides that, it doesn't matter which one is 5 and which one is 4. You could do 4 squared plus 5 squared, or you could do 5 squared plus 4 squared. It does not matter. What does matter is that since 30 is being plugged into here, I have to put the side length opposite there. All right. X squared equals, go ahead and tell me what x squared equals. To 3 significant figures, x squared equals 6.36. But if I were to write it out as an idea, it's like this, right? Remember that you then have to solve for x, so you need to take the square root of both sides. It's a step that a lot of students make a mistake on. So just remember that you need to take the square root of that final answer. And so a lot of times, to make sure that I don't make that mistake, I'll write out x squared equals this, so I can remember, oh yeah, okay, I need to take the square root. B is the exact same process, just with a different problem. So I'm not going to spend time going over it, but you are welcome to practice that on your own. The answer is 9.79 centimeters. So if you would like to practice that on your own, that's what the answer is, and you can see if you can do it by yourself. If not, come in and say, oh, what? And we can work it out. Okay, now we also want to be able to solve for angles. And sometimes we use law of cosines to solve for angles. Law of cosines does not give us an ambiguous case because it's side, 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 which guarantees you a unique and only one triangle, which is why you can use it to prove that 2 triangles are equal, right? So it's only when you have angle side, side that will have an ambiguous case. So the hard part about solving for angles using law of sines and law of cosines is that you have to isolate for the trig function, right? We talked about that with our law of sines. Here, we have a formula in our formula packet that's already isolated for that. So we just need to establish angle and opposite side. So this has to be C and this has to be uppercase C. It doesn't matter which one's A and B besides that. I'm going to label that A and B. Important part in a problem solving process, label your variables, right? That's something that could be very helpful for you down the road. So cosine of C, which is theta, equals, and then we have A squared plus B squared minus C squared all over 2 times A times B. And we get a decimal version of this. So we get cosine of theta is approximately 0.4545, and it keeps going on in that pattern for forever and ever. At this point, once we have a decimal approximation, we do our inverse and we flip them around. Please, please, please remember that you should not be using a rounded version. You should always be using the exact value. So scroll up and press enter. And go ahead and tell me what theta is equal to. Theta is about 63 degrees. And notice that I did not do it to three significant figures because it told me to do it to the nearest degree. So make sure you're paying attention to your instructions. That was a little bit tricky of me, but just make sure you're paying attention to the fact that nearest degree means to the nearest whole number in this case. So we would not be doing three sig figs. Here we would only be doing two. Again, I am not going to do B because it's the exact same process. And so it's just practicing to make sure you can do the exact same process. If you would like to do it on your own, which I highly recommend, the answer is about 93 degrees. Again, rounding it to the nearest whole degree. So see if you can do it on your own and see if that's what you get. And then we'll see how we feel about it. Okay. The application part of law of sines and law of cosines. We are revisiting bearing problems. And to be honest, this is more of the level of bearing problems that you will be seeing on the IB exam if they have a bearing problem. They will not be giving you a bearing problem that involves right triangles. We only had them last unit to prepare you for this moment. So there's a few things here that are important to know. That all north-south lines and all east-west lines are parallel. So no matter where you are, north-south will always be parallel. And we need to know our parallel line transversal relationships. That if I had a transversal going through here, this angle must be equal to this angle, and this angle must be equal to this angle. And you also got your converse angles and your same side interior angles, which must add up to 180. So if that's something that you're like, I never learned that, or if that's something that you're like, I learned that, but I don't remember it, that would be something that could be good to work on. I'll have that on your additional help links. Okay,